For this video, we're going to take a short break from matrices, and we're going to come back to them tomorrow. We're going to take a look at how we can use graphs to find maximum and minimum values. It seems kind of weird to kind of take a break from matrices to use graphs and find maximum minimums, but the idea is we're going to use a matrix to do this very same thing tomorrow. However, right now we're going to look at the basic case, and the basic case does not require the matrices. But I want to understand the basic case before we get into how the matrices help us with the more complex cases. So this idea of finding maximum and minimum values is called linear programming. And linear programming is basically a process to find extreme values of a linear function. Subject to certain constraints. So let's do a little bit of vocabulary. First, that word constraints. Those are the conditions of the problem that must be satisfied. Might say we've got a maximum of 40 hours to work on this project. That's a condition that must be satisfied. We'll also have this thing called the objective function. The objective function is the function we want to optimize. In other words, the function that we're looking for either the maximum or the minimum value of. We're trying to either maximize our profits, minimize our expenses, maximize our revenue, minimize the time spent, whatever the certain problem is interested in. And so the process we're going to follow in this basic case is the process, it's only one process, is the process that can be used for two variables. Because when we're graphing, we have two variables, the x-axis and the y-axis. What we are going to do is we are going to graph each constraint. And as we graph these constraints, they're usually going to be inequalities. We either want to be less than a value or greater than a value. So we're going to have to shade the graph to copy that. We're going to shade above a line, shade up for greater than, because if we want to be greater, we want to move up to infinity. And we will shade down for less than. Once all the constraints are graphed, we're going to end up with this region that's kind of like some type of polynomial. What we're really interested in that polynomial is to find the corners of the graph, because one of those corners is going to be the maximum, and one of those corners is going to be the minimum. We're not sure which, so we're going to plug the corners into the objective function and find out which one of those corners is going to give us the best value. So before we get into some examples where we can see this process of finding a maximum or a minimum, I first want to take a look at some tips on how we can use the calculator. Make sure we know how to graph these guys on the calculator. So we're going to do one quick example to see if we can figure out how to use our calculator for this. We're going to do x plus y is less than or equal to 24, x is greater than or equal to 2y, and y is less than or equal to 5. On the calculator, there's a y equals button in the top left corner. If you hit y equals, we get all of these equations that y could potentially equal. This means we have to get everything solved for y in order to type it into our calculator. So we'll go back. The first equation will subtract x from both sides, and we get y is less than or equal to 24 minus x. The second equation, we can divide both sides by 2. And I'm going to flip everything over at the same time because we like the y to come first. Notice the inequality points at y, so we're going to stay consistent with the inequality pointing at y, less than or equal to x over 2. And the last one already is y is less than or equal to 5. So on the calculator, we can type in 24 minus x, and the x button is right next to the alpha key in the second row, second column of the calculator. But what I want to notice is if we scroll over all the way to the left, we can actually highlight the line itself. Notice the line right next to y is blinking. That means I'm going to graph a line. If you hit enter, it'll say I'm going to graph a thick line. We want to graph when y is less than a value. Less than means we're going to shade down. So if I hit enter again, you see it's dark above now. Hit enter again, and now it's dark below. So if we come off of that, you see now the dark below the line by y1. That means it's going to graph below it. Similarly with our second equation, y is less than, again, we want to graph below the line. So there's above the line, and there is below the line. And the second equation was x over 2, enter. And the third equation is also less than 5, so we want to go below the line. First is the thick line, then above, then below the line in this case. Y is less than or below 5. Now we'll go to the window button. Before we graph this, we want to pick an appropriate window. Right next to y equals is window. And you see x min and max go from negative 10 to 10. Now for our example, and the examples we're going to be seeing, it's not going to make sense for our variables to be negative. So we're going to pick our minimum value to always be 0. The maximum value that I pick, what I generally do for the maximum value, at least to start with, is I pick the largest y-intercept. And if I look at my examples, I've got y-intercepts of 24, 0, and 5. The largest y-intercept is 24. So let's go with 24, and we'll make the y's exactly the same, from 0 to 24. That way, our largest y-intercept will just barely get inside our graph. Hit the graph button, and there's the first line, 24 minus x. Here is the second line, x over 2. And here's the third line, y is less than 5. Now what takes a little bit of looking at as we look at this graph is we want to find the double shaded area where everything overlaps. You see that's kind of the bottom center area. So I'm going to draw a picture of this graph. So looking at the graph, we had one line that just kind of came down. We had another line that came up slowly, and another line that came in flat. And where everything was overlapping and shaded was in this area down here at the bottom. That's going to be the area we are interested in for maximizing some type of objective function. We're interested in the corners of this function. The first corner we see right here in the bottom left corner, and that's obviously at the origin, so that's the point 0, 0. There's two more corners that we might have to dig a bit to get. And then finally there's this last corner. We don't know what the x value is, but the y value is certainly 0. There's no vertical movement. To find the x value there, we can probably figure it out because we see that that corner comes off of the one with the largest y-intercept. The one with the largest y-intercept, that was 24 minus x. If we make y equal to 0, that's what y is at that value, y equal to 0, we have 0 less than or equal to 24 minus x. Add x to both sides, and we can see that's going to intersect at 24. So the x coordinate there is 24. We can usually pull x coordinates and y coordinates off of the intercepts pretty quick just by inspection. Now the other 2 points we might have to do a little bit more work for. But that's where our calculator is going to come in handy, because our calculator has an intersection feature. If we hit second, and at the top above the trace button it says calculate, we can calculate number 5 says the intersection of 2 lines. When we do, there is a blinking dot that you see there, and if you scroll that blinking dot around, let's scroll, it's going to go down a line until it gets kind of close to where the 2 lines intersect. A lot of stuff going on there, but you can see that blinking line. Hit enter, and it's going to jump you to another line. That's not the line that we're looking for, though, because we want to intersect at that point on the right side. So if I hit up, whoops, that's the curve I was already on. Sorry, if I hit down, and down, it'll take me to another curve, and now I'm right on top of that spot. Enter. Then it's going to ask me to guess where the intersection is, right there. That's why I got on that spot. And it'll tell me the intersection is at 19, 5. Those 2 graphs intersect at 19, 5. We can find the other point in much the same way. We hit second, calculate, and scroll down to number 5, or you can just type in the 5 to find where the lines intersect. Scrolling, you'll see this scrolling is scrolling up the line. That's not the line I want for the other intersection point on the left side. So we hit down to jump onto another line, and that's the one that's going to hit it right about there. Hit enter. The second curve, that is the second curve, so we hit enter. And we guess, so we hit enter. And that other intersection is at 10, 5. 10, 5. And then, now that we have these 4 points, we'd be able to find the maximum and the minimum value, because one of these points is going to be the maximum if it exists, and one's going to be the minimum if it exists. So that's how we can use the calculator to help us with the graphing. Let's actually do some examples. We'll do one maximum example and one minimum example. How about this? Let's say you have 240 acres of land on which to plant corn and oats. You have 320 hours of labor available. To raise this crop. Turns out that corn takes 2 hours of labor per acre, and oats take 1 hour of labor. You earn a profit of $40 per acre for corn and $30 per acre for oats. How many acres of each should you plant to maximize profit? Well, you make more money for corn, so should you plant all corn? Problem is corn takes a lot more work, and so you might run out of time to get all of the corn going. So this is a nice linear programming example where we're trying to maximize our profit based on these certain constraints. We are constrained by land, and we are constrained by time as we try and maximize our profit. Our constrainment by land is we have 240 acres of land. So we can't plant any more than that. That is our maximum. So the amount of corn plus the amount of oats, I don't want to use O because that looks like a 0. I'm going to use A, oats. Corn plus oats has to be less than or equal to the amount of land we have, the 240 acres of land. That's our first constraint. Our second constraint is the labor. We have 320 hours of labor available. We don't have to use it all, but we can't go above it. Corn takes 2 hours and oats take 1 hour. So we've got for two corns, 2 hours for the corn plus 1 hour times the oats have to be less than or equal to the maximum 320 hours of labor available. The profit we earn is, well, I'm going to highlight that in green. We earn a profit of 240 for corn and 30 for oats. Since this is what we're trying to maximize, I'm going to use the letter Z. Z is always what we're trying to maximize. Z is equal to 40 for the corn plus 30 for the oats. Now we have our equations, but we can't put them in the calculator until we solve them for one of the variables. Now I usually look at which variables would be easiest to solve for. We're only going to graph the inequalities. And looking at the inequalities, it looks like the A's are going to be easiest to solve for. So we're going to get the A's alone by subtracting C from both sides. So the first inequality is A is less than or equal to 240 minus C. and subtracting 2c from the second equation. So a is less than or equal to 320 minus 2c. Then what I'll usually do is I'll write down in a different color, I'll write down what order the variables are going to come in. Because I don't have a and c axis, I have x and y axis that I'm more used to. The variable you solve for on the left side, that a is always the second variable that comes in. A is going to be the second variable. C is going to be the first variable on my graph. That order is very important, or I'll plant the wrong type. If I want 30 and 50, I'll plant 50 and 30, and then I'm backwards and I don't maximize my profit. So let's see if we can do that. Let's hit the y equals button. We've already got lots of functions in here. We're going to hit clear, enter, clear, enter, clear, enter. That takes them out. And the first inequality is just 240 minus the variable. And the only variable the calculator will take is the x, right next to the alpha. But that's okay. We're just going to use x. And since the a is less than that, we want to shade below that line. So we'll hit enter, enter. That's above the line there. Now we're below the line. The next equation is also less than. We want to be below the line, so we'll hit enter on the line until it shades below. And this is 320 minus 2 times the variable. Once those are in there, we go to our window. Now, it doesn't make sense to plant negative corn or negative oats, so we're going to keep our minimums at 0. That generally never changes. The maximums, though, I like to pick for my maximum values the y-intercept, the biggest y-intercept. And looking at our equations, we have y-intercepts of 240 and 320. 320 is the big one, so we're going to type in 320 for the maximum, for x max and y max. Now, we might have to change that later if we look at the graph and feel like we can't see what we need to see, but for now, we'll hope that's enough. Hit graph. There's the first line. There's the second line. Notice we get this four-sided thing in the bottom left corner. That's the place where we double shaded. That's what we're going to be interested in. So I'm going to sketch a very rough sketch of this graph so we have it for our records. The first graph was from the top down to about the middle. The second graph was from near the top down to about here. It doesn't have to be perfect. But what I really want to be able to do is say where the double shading was on that graph below is right here. I should do this with a highlighter because it's thicker. Anywhere in that region, all of the constraints of land and time are satisfied. Our maximum and our minimum of profit is going to happen at one of the intersection points of this shaded region. There's 4 of them we have to consider. The bottom left is the easiest to find. That's 0, 0. The top left we should be able to find. Notice that's the y-intercept. It's the smaller y-intercept, not the bigger one. Our smaller y-intercept is 240, just looking at our equation. So we have 0, 240. And the other one's an x-intercept. We know the y value is 0. And this is coming off of, if I follow the line, the bigger y-intercept. It's coming off of the 320. So I can really quick solve. The output is 0 equals 320 minus 2c. If I add 2c to both sides, 2c equals 320. Divide by 2. The c value there is 160. So the x-intercept is 160. The only one we need to do a little bit of work for is this one in the top right. And we're going to have the calculator do the hard work for us by hitting second, trace, which gives us the calculate menu. Number 5 is to find the intersection. Gives me a blinking dot on the line. We're going to scroll over until we get in the ballpark of the intersection. Hit enter. It's going to jump me to another line close to where I was. Does that look like about the intersection? Yes, it does. I'll hit enter. Then it wants me to kind of guess where the intersection is. I'm already there, so I'll hit enter. And the intersection it's saying is at 8160. 8160. And so these are my four possible points: 0 to 40, 8160, 0, 0, and 160, 0. 4 possible points for my maximum and my minimum. Now the minimum probably is pretty obvious just looking at it. If I make, remember my constraint equation, $40 for every corn and $30 for every oat. If I plant nothing, I'm going to end up with nothing for profit. That one is, I'm pretty sure that's not my maximum. So we don't even have to play with that one much. So basically what we're looking at is the case where we plant all corn, all oats, or a mixture of the two, 80 corn and 160 oats. So when we plug this first point in, the objective function says we've got 40 times corn plus 30 times oats. 40 times corn, which is 0, plus 30 times oats, which is 240. Well, 40 times 0 is 0. All we have to really do is 30 times 240 to get $7,200 profit. If I plant all oats, I make $7,200. What if I plant 80 corn and 160 oats? Well, that's 40 times 80 plus 30 times 160. 40 times 80 plus 30 times 160. I make $8,000 profit with that option. We know 0, 0 makes me no money. That's our minimum. We don't care about that. But what about 160 corn? We make 40 times 160 plus 30 times 0. Would it have been best to plant all corn? It makes us the most money. 40 times 160 only makes us $6,400 because of how much more time the corn takes to plant and raise. It's actually the least profitable option to go all corn. The most profitable option we can see now is the $8,000 profit. So our advice is to plant 80 acres of corn and 160 acres of oats for a maximum profit of $8,000. And that's how we can do linear programming to maximize a function. We graph the constraints, find the corners, and then plug the corners into the objective function. Gives us the maximum. It also gives us the minimum. So we could have done a minimum problem. Let's try one. Let's say a rancher is mixing 2 types of food. He's got brand X and brand Y. for his cattle. Each serving needs at least 50 grams of protein. And 30 grams of fat. Brand X has 15 grams of protein and 10 grams of fat. And cost 80 cents per unit. Brand Y has 20 grams of protein and 5 grams of fat, and it costs 50 cents per unit. So the question the rancher is interested in is not how to munch, but how much of each should he buy to minimize the cost. Oops, too far. Again, this rancher wants to make the food, minimize his costs, but he's limited. He's got certain constraints. He is constrained because he needs a certain amount of protein for his cattle and a certain amount of fat for his cattle, and it's going to end up with some type of cost associated with it that we want to minimize. So cost is what we want to minimize. That's our z equals. The other two are going to be the inequalities that we need to graph. So let's look at our limitations on protein. Protein. We need at least 50 grams of protein. And X has 15 grams of protein. And brand Y has 20 grams of protein. So X has 15 grams of protein for each X, plus Y has 20 grams of protein for each Y. That has to be greater than or equal to, because we need to have at least 50 grams of protein. More than 50 is okay, but we need at least 50. Similarly, we can make a constraint for the fat. We need 30 grams of fat, at least. X has 10 grams, and Y has 5 grams. So for the fat, we get 10 grams for every X, plus 5 grams for every Y, and that has to be at least greater than or equal to the 30 grams of fat the cattle need. Finally, the cost, that's what we're going to try and minimize. Brand X has 80 cents per unit. Brand Y is 50 cents per unit. So the cost, we get 80 for every X plus 50 for every Y. Let's go ahead and solve these for Y, just because we're used to solving for Y. So we get Y equals mx plus b form. It's going to be a little bit more work. Let's see, if we subtract 15x from both sides, since we should be really good at solving by now, I'm going to kind of cheat and divide by 20, right? So the first inequality is y is greater than or equal to 50 minus 15x over 20. The second equation, we'd start by subtracting 10x, and then we would divide by 5. So y is greater than or equal to 30 minus 10x divided by 5. And just to make it easier to type in our calculator, we'll go ahead and divide each part by 20 and by 5. So 50 divided by 20 is 5 halves minus negative 15 over 20. We can reduce that by dividing by 5, gives us 3/4 x. The other inequality, 30 divided by 5 is 6, minus 10 divided by 5 is 2x. So that's what we're going to graph in our calculator. Go to y equals. We'll hit clear, enter to clear out the old inequalities. Our first inequality is 5 halves, that's about 2.5, minus 3 over 4x. The second inequality, 6 minus 2x. And scrolling over so that we can shade the correct direction. Notice these, the y is greater than a value. We want to shade above the line. So hit enter until the part above the line is shaded. Be careful not to grab the thick line. We want above the line. Don't get those mixed up. Now we'll hit the zoom button. Or I'm sorry, the window button. Wrong button. Now we hit the window button. Again, we're not going to have negative of brand X and negative of brand Y. So zeros are good for our minimums. For our maximums, I like to always pick the y-intercept, the biggest y-intercept. We have a y-intercept of 5 halves or a y-intercept of 6. 6 is bigger than 5 halves. So we're going to pick our maximums, both x and y maximum. We're going to set them to 6. We might have to adjust them, but let's see. Here's the first one, graphing above. There's the second one, graphing above. And it looks like they intersect right near the end. I'm going to actually adjust my window here so we can get a better view of that intersection triangle down there at the bottom. So it looks like I can cut my x, that's my x coordinate across the bottom. Looks like I can cut it down a little bit. So I'm going to go to Window, and the x max, I'm going to cut it down to 4 and hit Graph, just see if that gives me a better looking graph. So there's one, and there's another. Okay, so we get a kind of idea what this is looking like. So the first one came down from the top. The second one came down a little less steep, and I'm going to kind of exaggerate the point of intersection. And this time the double overlap of the shaded regions was above, because we were always greater than this time. Because it goes on to infinity, we're going to have corners at the top, at the bottom right, and also right in the center. Again, the intercept should be easy to find. The y-intercept especially, that's the biggest y-intercept of 6. So we have 0, 6. The x-intercept down at the bottom, we know the y value is 0, and that comes off of the one with the smaller y-intercept, just by observation. So if we plug 0 in for y, 0 is equal to 5 halves minus 3/4 x. Let's add 3/4 x to both sides. So we get 3/4 x equals 5 halves. Multiply by the reciprocal of 4/3. And x is equal to, 4 over 2 reduces to 2, 10/3. So 10/3 is the x value. Now we just have to find this last point in the center. Our calculator can do the dirty work here. We hit second, calculate, number 5 for intersect. And that gives us our little flashy dot that we can scroll over, and the numbers are kind of in the way. We'll do our best we can. It's right about there. Pops us to the second curve, enter, right about there. Our guess, right about there. It's going to intersect at 2.8, comma 0.4. 2.8, comma 0.4. And so, making sure we know we solved all of these for y. That means y is the second variable, x is the first. So our options were 0, comma 6, 2.8, comma 0.4, and 10/3, comma 0. We just have to test each of these in the objective function to see which one gives us the biggest value. I'm sorry, not the biggest value. We're talking about cost. We want to minimize. We want to find the smallest value. So 80x, 80 times 0 plus 50y, 50 times 6. 80 times 0 is 0. 50 times 6 is 300. So that's our cost with the 0,6 option. 2.8, comma 0.4, we have 80 times 2.8 plus 50 times 0.4. What's that going to cost? Second quit to take us back to the calculator screen. 80 times 2.8 plus 50 times 0.4, $244. That's a little bit better cost. And the last one, we have 80 times 10/3 plus 50 times 0, which is just going to be 0. So 80 times 10 divided by 3. The cost there is $266.67. $266.67. We're trying to minimize our cost. The minimum cost, the smallest cost, was that second option where those 2 points intersect. So we're going to advise this farmer to buy 2.8 units of brand X, 0.4 units of brand Y for a cost of $244. That'll be his minimum cost, but still satisfying all the constraints, giving the cattle plenty of protein and plenty of fat. That's how we maximize or minimize our objective functions. So this form of linear programming, graphing them and finding the intersection points, works great with two variables. And that's what we're going to look at tonight. Get really good at translating the problems into the constraints, into the objective function, interpreting the results. And then tomorrow we're going to go back to matrices to see how matrices allow us to find points when there are more than two variables that we're looking for. But for now, take a look at the homework and come to class with any questions you might have.